hear me fine. Okay, I'm Luca Pavarino from the University of Pavia. And welcome then to the last plenary talk of today. It will be given by Professor Gernot Planck. He's a professor of computational cardiology at the Medical University in Graz. He got his PhD in 2000 at the Technical University of Graz. And then he spent, he was visitor in several places, among which Johns Hopkins and Oxford, before becoming a professor in Graz. And his basic research interests are the development of computational methods for modeling total cardiac functions and their application to anatomical accurate and biophysically detailed models. And today he will talk to us about this new thing of digital twins. So we're going to learn about an automated workflow for creating digital twins in cardiac electrophysiology. Okay, Gernot, the floor is yours.
Thank you, Luca, for your kind introduction, and thanks to Alfie for having me. I'm trying to share my screen, but oh, sorry.
The host has to do it.
No, you have the permission.
You can do it.
I had to. Sorry. I guess I have to reconnect because it was asking me for some permissions. Just a second. I'll be back in a minute.
Sure.
I had the same problem several times indeed.
Oh, the host has deactivated sharing of the screen.
Yeah, that's what I see too. We need to ask Luca Paglieri maybe to enable.
Yeah, I can. Okay. I will enable again. See if you can now.
Yes, I can.
Great.
Thank you.
Okay.
So, sorry for the delay, but I'm getting used to that. Whenever I'm giving a talk in Milano, there's some kind of glitch in my presentation. Today, I'm going to talk about automated workflows for creating digital twins of cardiac electrophysiology. And in the context of this talk, I'm talking about one-to-one mapping cardiac digital twins. These are digital replicas of patient hearts derived from clinical data that match like for like all available observations. And all available, I mean all reasonably feasible observations like ECGs or body surface potential maps. So do we actually need digital twins? Let me start with that question. So in basic research, I think that some recent work we were investigating the spontaneous calcium release, how it's generating ectopic foci, and how it's initiating a re-entry. So this is a model of a rapid, and we don't need a digital twin for that. So it's good enough to parameterize that model with data from literature. Whether this really very rapid existed or not does not really matter. In other scenarios, application scenarios like medical device development tool, in some our recent work, so we were interested not just in gaining mechanistic insight, but also in testing the safety or efficacy of a given device, of a transvenous ICT setting, or of different adaptive protocols for anti-tachycardia pacing. In this case, it should be a plausible person, a plausible patient. Ideally, we would like to test in a virtual cohort where we have some anatomical and physiologic variability. So here, digital twins could be useful. Even more demanding is the applications like software as a medical device. The recent one here shown from Natalia, the virtual arrhythmia risk prediction. So here, digital twins might play a bigger role, although in this application here, no personalization has been performed. So there was no electrophysiology information used. This is definitely not a one-to-one mapping digital twin, but it has been shown that these simulations are of predictive value. So this was a CRP stratification problem. For CRP optimization problems, it might be a different story, and digital twins might play a bigger role. So when we go from basic research to software as a medical device, we go from a couldn't care less to a must-have or really nice to have scenario. The other question is, if we want to have digital twins, how can we build them, and how accurate and how efficiently can we build digital twin models? And this is the main focus of my talk today. So there are challenges in building digital twin models, particularly if we talk about electromechano-fluidic models. Here we have an electrophysiology problem. This is driving EP, giving us physiological signals. We can link that with the deformation problem. This is bidirectional link. This drives deformation nicely, and we can also couple that with a fluid flow problem. This is an FSI problem, and we can compute a heartbeat. So I'm not saying it's straightforward, but in theory or in practice, we're able to do that. So we have now a model of a heartbeat. If we want to create a digital twin, the problem is we want to build the model of the heartbeat of this given patient, and then we have to identify a lot of parameters. So these parameters cannot be measured in vivo. They cannot be measured ex vivo neither. So we have to directly, infer these parameters from measurements which we actually can perform. In this talk, I'm going to focus on these parameters here, how to identify these, because these are relevant for electrophysiology. So what are the challenges of building one-to-one mapping teams? So there's a lot of uncertainty in this problem. So we have geometric uncertainty on the anatomy. Maybe this is the minor problem. But if you run a forward model, electromechanics, for instance, we have complex input uncertainty like heterogeneities, fiber architecture, conduction system, and so on. We have uncertainty in conditions, initial conditions, boundary conditions, limit cycles, and so on. Parameter uncertainty is definitely huge as well. And there's observational and residual uncertainty on the data we are measuring. So no heartbeat is like the next one. So this causes initial residual uncertainty. So if we measure some data, these all together constitutes input uncertainty. We have our measurements and we want to calibrate that to our forward model. So if we compare the two things, no matter how hard we search the literature for the best measurements, if we use these, this is not going to add up. This will be very different what we are seeing. So we have to go back and calibrate our models. There are essentially three ways of doing that in my view. We can do optimization. Very nice. The problem is here we have to compute a descent gradient direction to reduce our loss, which can be challenging. Sampling is conceptually simple. We just sample our physiological corridors to find a good match. But for that, we need very, very efficient forward models. Or we have the ability to generate really a lot of data, then we can build a regression model using machine learning, for instance, to approximate the inverse function of our forward simulation tool. So this might be a viable way to go, at least to get an initial idea of the parameterization, if and only if if anatomy is not playing a key role. Otherwise, you have to learn a regression model over and over again, and you're not gaining anything. If we want to make clinical predictions, we also need to estimate the confidence in our predictions. So how confident are we that our predictions are correct? And here we need uncertainty quantification. We need to characterize our input uncertainty, determine how this maps forward the uncertainty in our outputs, and ideally we decompose also the variance so that we know which parameters contribute how much to the overall uncertainty of our forward model. So what we are working on since a while now is building virtual cohorts of electrophysiological twins for in silico clinical trials. So here I'm reading the definition according to the Jenner roadmap. So ICDs is the use of a virtual cohort of individualized computer modeling and simulation in the development or regulatory evaluation of a medical device or intervention. So kind of a lengthy definition. So what we're working on here is we want to use clinical inputs, strictly non-invasive clinical inputs. These are images and ECG or body surface potential maps when available. So we perform multi-label segmentation, and this is a very important step. We need a very clean, a very good multi-label segmentation, because only this allows us to automate all the subsequent steps, because all the subsequent steps will be operations on labels, automated operations on labels. So we can generate a mesh, we transfer the labels on the mesh, we functionalize our model. That's the feature vector we're going to use to represent the problem, in this case electrophysiology. We do a forward simulations, predict our ECG, compare, and go back and loop. We loop until we find a really good match where we are convinced that the problem we are looking at in our model is the same problem as we are looking at in a given patient. If we are confident, we can use that, move forward, build virtual cohorts for different therapies, implant virtually different devices, and do device in silico trials. So to achieve that, we really need to achieve a high degree of automation for obvious reasons. Otherwise, this will kill any lab, and it's a very error-prone and costly procedure. And we need a fully abstract functional model description to be able to achieve an unattended machine-driven manipulation of all features. So no manual interaction whatsoever with the model. So to get a good ECG, we need, I'm talking mostly about QRS now and T-wave, so the ventricular portion of the ECG. We need to match a ventricular electrophysiology. So this can be certainly done by electrical mapping. Here you see very nice electrical mapping experiments at the University of Utah. And what we need to match is the activation and the repolarization patterns. So this is characterized at any point in space by an action potential, so an upstroke occurring and a downstroke in space. This translates to the wavelengths. So the upstroke translates to the wavefront, the downstroke is the wave back, in between there's the plateau. This is a severe simplification of reality, because the wavelengths, actually conduction velocity and action potential duration, both are functions of space. These are not scalars. So for arrhythmia studies, it's important to match that, because the electrical size determines whether we can induce an arrhythmia or not. If you look at that problem, we have a certain conduction pathway, and if we divide that physical size of that pathway with the wavelengths, we compute the electrical size X. If this is larger than 1, we can induce, like in this case. For the ECG, it's now important that the wavefronts are of the right size, at the right spot, at the right time. Otherwise, we don't get QRS right. And the same is true for the repolarization or the wave back, which is shaping the T wave. This makes ECG modeling very hard, because you have to get all the individual components right to get the overall global measure right. And ECG is very sensitive. If I were to perturb that wavefront, I would see that immediately in the ECG. So now none of the parameters I'm talking about here shows actually up in the equations we are using. So how are we gonna deal with that? So first of all, we need to initiate activation at the right sites. So initiation is important. So we use this like kind of Purkinje system to drive the activation pattern. And if we use a Purkinje system, we get a very fine-grained activation pattern. So we need to make the wavefronts move at the right velocity. If we look at a simple 1D model, we can see immediately more or less that the conduction velocity depends on certain factors. So we need to fix these factors to get the conduction velocity right, that the wavefronts propagate the right way. So certainly sodium channels are also playing a role, also influencing the conduction velocity. So with these, we can assemble a feature vector for activation, and this is going to shape or determine or govern the QRS complex of our ECG. We move on to repolarization, and as Professor Sugura mentioned before, most definitely we have to fit activation sequence first, because repolarization depends mostly on activation. Then it also depends on intrinsic heterogeneity and action potential duration, but also on diffusion. So if you look at the two cases here with diffusion on and diffusion off, you can see that diffusion acts to smooth out intrinsic heterogeneity. So this is also playing a role, and this gives us another feature vector where we control the T-wave. How are we going to functionalize the model? So these are the factors playing a role in the genesis of the ECG. So we need all the connectivities in the torso. We need the cardiac active conduction system. So here we're using an abstract fascicular system as simplification. So we just assume we have fascicles of a given location size and given intramorality. And then we have a fast conducting layer to approximate the His-Purkinje system. So our model has fibers, and we have some heterogeneity also in repolarization to get the T-wave right. This can be label-based or it can be function-based. Function-based gives us better control over the distribution of action potential heterogeneity over the whole domain. Next, we need a reference frame, a navigation system for the heart that gives us an idea, an anatomically meaningful idea of moving around and in the heart. Here we use universal ventricular coordinates as developed by Ed Wigman's lab, and we also use universal torso coordinates to control location everywhere in the torso. With that, we define a geometric mapping. So we can take any entity defined in a heart, like an infarct, map it into that space, map it back onto any other entity, or map it back onto the same heart, but control in UVC space where we want to map it back. We can also define artificially any entity in the UVC space and map it back onto the heart. And as you can see, it's obvious what's going on here. So we have very good control. This is a fascicle, and we are controlling the location, we are controlling the size, intramorality, and transmural extent, and all the parameters. So all these space-dependent parameters become a function of space, which we can manipulate easily. And this allows us to achieve full automation in a parameterization loop, because we never interact with the mesh. We manipulate everything abstractly in a UVC space. So now we need a fast-forward model. Initially, we developed that as a driver for cardiac electromechanics, but certainly for ECG, the activation sequence is as important. Standard reaction diffusion models are not very well suited for this forward problem because there's this nasty term in here, which forces us into high spatial resolution. So if you want to get our source model right, make sure the wavefronts are propagating at the right speed, and this is also showing up on the right-hand side of the elliptic portion of the bidomain. This is important for computing extracellular potential fields from where we derive in the ECG. So what we're doing to circumvent this problem, we solve first another problem. We solve the diagonal equation. This gives us activation times everywhere in the heart. Use an analytical formulation of the foot of the action potential as a stimulus current to drive activation. So we add this term in here, and all of a sudden we can run the same problem almost in real time. So we are solving a more complicated problem, but the formulation lifts the constraints on spatial resolution. We can go for very much coarser resolutions. So the gold standard of ECG computing is the bidomain model. As you can see here, it computes phi-E everywhere, but it requires high resolution. So this run, for instance, used 576 cores, took 8 hours to compute, produced 125 gigabytes of data, which must be downloaded and analyzed. Sounds like fun. So direction iconal model with pseudo bidomain does the same thing. It ignores some minor loading effects, path loading, curvature effects, initiation, collision sites, and so on. There will be a slightly different motion of the wavefronts, but we can go in a very coarse resolution, and we can do the same thing in 30 actions, 20 minutes on a desktop computer. If we are only interested in ECG, we want to know the potentials only at these locations, we go for the reaction iconal with lead field, the RELF model. We solve the lead field equation, we inject unitary current here, destroy it elsewhere. We solve, do one elliptic solve. We do a monodomain reaction iconal forward, which is actually shown here. The simulation is actually faster than a visualization, and then we do this convolution. It's basically a matrix vector product and a pointwise vector, a very cheap operation. One of these operations per ECG and time step, which is essentially for free. we get the ECG and the EGMs, or electrograms, wherever we want. And the advantage is we can do this much faster. We can go from 8 hours to 6 seconds. So you may say, okay, but this is not the same thing. The ECGs are probably not much worse. I can assure you this is not the case. So here you see a 250 micrometer grid reaction diffusion, the RELF model, both 10^2 and the RELF with Mitchell-Schaefer. You can see the ECGs pan out within the limits of clinical data uncertainty. That's something we have to keep in mind. This is the same. So the differences here in the T wave, these are minor glitches in V2 and V1. These are minor glitches, ignore that for now. So we can then go to coarser resolution. We go down to up to 1,500. You see some minor changes, attenuation in the magnitude, but the overall morphology is preserved. We can even turn off diffusion without any major differerences. So what are the advantages? The RELF model produces gold standard bi-domain ECGs, executes with close to real-time performance on a desktop computer, and thus this renders it suitable for ECG-based parameterization of EP twins. So here's how we do that. So we have our target measurements, which is in this case a QRS. We have our model, which we functionalize. We're not functionalizing all the parameters, so some we are treating as fixed. So we're using 5 fascicles, and fibers and connectivities we don't touch for now. We're also not using a Purkinje system, using something simpler, as Ed alluded before, a 5 fascicle system. So it has a septal fascicle, a posterior fascicle, and an anterior fascicle. In the LV, in the RV, we have a septal fascicle and the moderator band. For the T wave, we use a weighted gradient of the known gradients, which is transmural, left, right, apico-basal, anterior, posterior, and we give them weights. And then we squeeze the function into an APD map where Amax and Amean are minimum and maximum action potential relations we need, and we can estimate that from our T wave. This needs to be mapped then onto the ionic model, which is actually fairly straightforward. So we get our initialization and define a physiological corridor about our initialization, and then we can start sampling. Here we're doing something stupid. We're just moving around a little fascicles to see how the ECG reacts to these perturbations. And then we get a measured ECG, which we can compare then. We could extract features for comparison, but we're comparing the whole signal. Both signals are filtered the same way with clinical settings. We do some time alignment and some scaling, but to preserve correspondence in time and also in magnitude. And then we measure the similarity with L2 norm, correlation coefficient, dynamic time warping. There are also candidates. And then according to the loss, we rank the quality of our fit. So here is one case. We ran 10K samples on fitting the QRS and about 10K samples on fitting the T wave. So here you see the results. As you can see, the QRS fit is fairly good. There are some minor deviations. Also keep in mind, these are filtered signals, and the simulated signals are only 450 milliseconds. And at the end and at the beginning of the signals, you get a little bit of a filter artifact. The T wave is not ideal for obvious reasons, so we did not find a really good match in the T wave. But the model replicates QRS morphology, and many known ECG features are progression as disappears between V3 and V4 and all of these features. The regularization model as sum of linear gradients is definitely too simplistic, so we could not find a good T wave with that model. But additional invasive data could be helpful to better constrain the model. I'm gonna talk about briefly at the end of my talk. What is the influence of anatomical variability? This is something I'm interested in. So what we did is we used that fitted model, the activation and the regularization setting of model S62, and deployed it in all other subjects. So objectively, all the subjects have the same EP, only the heart and the torso anatomy are different. So here are 12 of our 13 cases. So as you can see, they have the same settings, but they produce slightly different ECGs. So there's this one dodgy one. This one is S68. Okay, this one, for non-obvious reasons, is different. Let's remove that. And then we can see the same settings produce comparable ECGs. So can we use then a generic activation repolarization settings only models? That means does a matched 5-fascicle Dürr setup produce correct individual ECGs? And this is actually not the case. Here you have case 62. We use the same system. In 63, it produces a comparable ECG, but the ECG of that subject is quite different. Then let's look at a female one. Here also, it's not a good fit to this subject. Although if you look at lead 2, all 3 cases have pretty much the same electrical axis. And also if you look at the dynamics of that, it's not easy to pick up what is causing the differences. So this is work in progress. And also so now let's wait, you see repolarization. Also, if we compare against the dodgy one, so you get some ideas. The heart relative to the torso is fairly large. The inclination angle, the anatomical axis is different. The size of the lungs is different. So there are differences. So this needs to be explored to fully understand what is really relevant for getting a good ECG. So every case in the study would need a different, completely new, different sampling strategy. So can we do this at scale now? The bottleneck in our pipeline is segmentation. So we have an automated CNN-based segmentation, which works very well, does a very good job, but to adhere to our quality standards, most often we need some manual corrections, and it can take up to 4 hours to build a really good model. So once we have done that, the rest is automated. So here are some performance metrics. So like meshing, the 1 millimeter resolution is the standard model we're using for this type of work. Meshing takes about 10 minutes. The total model building it's another 10 minutes, about where the UTC generation takes up most of the time. Simulation, the first run takes 169 seconds, but only the first one we are computing the lead field. If you're not changing fibers or conductivities, we can reuse that, and then the cycle time is only 6 seconds. So on a desktop, in 6 seconds, we can produce a gold standard vitamin ECG, clinical ECG. So the 5-fascicle system approximates a sinus speed fairly well, but it's not suitable for basing therapies as it doesn't allow any retrograde activation like a Purkinje system would. And the other issue is the fascicles need to be stimulated. So there's a timed activation, and this, if not done very carefully, can cause ECG artifact, which is annoying. So what we're doing here is we first use our 5F disk model to approximate the ECG. Once we're happy with the ECG, we grow a Purkinje system into the labels. So this is done, Ed explained that in detail. This is work done at in Ed Wigman's lab. And then we have the Purkinje system, which will wire up according to certain rules and link it to an AV node to drive activation. So we can compute then activation in both models. And as you can see, the activation maps are nearly identical. There are some subtle differences. You have more structure, more fine granularity on the Purkinje system, evidently, as this, which is obvious. But if you look at the ECG, so his Purkinje and 5F, they match up. So we can match first with the simple model and then replace it in less than a minute with the Purkinje system. And we also get rid of some artifacts, like here, if these are clearly not S or Qs, these are stimulation artifacts. In the Purkinje system, you don't have that. Experimental validation of the model, this is ongoing. This is work with the people in Utah with an experimental torso tank setup. Similar, probably gonna do similar work with Jason Bayer and Ed Wigman in Telluric. They have a comparable setup. So here they can do a really high resolution 3D mapping, and this will help to better constrain the search space. So they put plunge needles into the heart at a high density. This gives you a much better idea where is activation intramurally, where's it actually starting. So you get a better idea of the intramural activation sequence, and we can also validate ECG model under various pathological conditions like ischemia and chronic infarcts. So it's very straightforward to take this model, build a simulation setup with the plunge needles in and ECG locations. We take this forward and do exact the same pipeline here with the pacing side. This is simpler, this is not sinus, this is really pacing now, and then we can compute forward and get an activation system. So they did not bother to segment the atria, so the atria just this dodgy blob here at the top, but the ventricles are nicely segmented. So this is a simulation we did last week without, essentially without any tuning, so with some default settings, and I was really blown away how good the match was without any tuning. So evidently we're missing some details here, like the double notched T in leads 1 and AVL and so on, but the overall morphology is in place. And this is also the reason why PVCs or paced activations are much easier to match than a sinus activation. Okay, let me conclude. So creating EP digital twins that replicate all available observations for a given physics, in this case only EP, and as observations we have ECG or body surface potential maps, within the limits of data uncertainty is clearly becoming feasible. For building EP twins, the RELF model predicts ECGs with gold standard accuracy and real-time performance, and as such can be used for model parameterization. So this model is really a game changer for us, because on a desktop you can play around interactively and test a lot of physiological ideas. A high degree of workflow automation can be achieved, and this automation allows building of EP digital twins at scale, and thus actually to provide virtual cohorts which we can use in ICDs. These capabilities are essentially developed. The weak part, and I should mention that now, is we need much more advanced optimization or ML-based methods to further accelerate the functional twinning. What we're doing so far is stupid brute force sampling. So we need 20,000 or up to 100,000 sample runs to find a good match if we do it blindly. And although one run takes only 6 seconds on a desktop, this adds up to 1 day. You can scale this down on a supercomputer, but if you go to supercomputers, and that is not the point of, I think for clinical modeling, this is not the way to go. The software we are using, so not everything I was showing is implemented in OpenCarb, but the basic framework we're using, everything builds on OpenCarb, which is available now, freely available as source or binary distribution also for academic purposes. And let me acknowledge the funding, and let me thank my lab for doing all this work. What I've shown today is pretty much the PhD thesis project of Kali Gillette. Okay, that's it. If you have any questions, I'm certainly happy to take them.
Okay, thank you very much, Gernot, for this great talk. Wonderful material. So the floor is open for questions, comments. Maybe meantime, maybe while people...
Olaf Dössler is asking a question.
Ah, okay. I don't see it in my chat. Can you see it? Can you read it?
I can see it, yeah.
Okay.
It's under
participants. So if you click on the participants, then the ones that raise their hands shows up. So thank you, Gernot, for this excellent talk. I really enjoyed it. And my question is about you have shown that the reaction eigenvalue equation delivers the same results as the full biodomain, but on the long run, we want to look at the patients. And does this, you showed it for the sinus rhythm.
Yeah.
And in the last part of your talk, you mentioned that premature ventricular contractions are even maybe easier. But there are other diseases, for example, infarction, a rotor, whatever. Do you think that you can also use this, speed up the electrophysiology simulation with the reaction eigenvalue equation, even in case of strange diseases?
So for for most diseases, this is not a limitation, like ischemia, infarct, and so on. If you talk about arrhythmias, that's a very different story. So, but this is ongoing work. There's a lot of work ongoing in a collaboration with Smart and Bishop, and we can do the same thing for ventricular tachycardias in real time. So this is not a limitation, but this I have not disclosed because that's currently under development. So you can extend these ideas. It's not, if you look very, very carefully, you can spot differences between the bidomain and the RELF model because it does not account for path loading. It doesn't properly account for curvature effects, for collision sites, initiation, and so on. But usually on the body surface, you're far enough away from the sources that these subtle differences do not show up. If you measure electrograms and use the same approach for intracardiac electrograms, so it might be more, that is a different question. That might require more work, but not on the body surface.
Thank you.
Okay, I see a question from Pasquale Africa, please.
Yes, first of all, thank you, Professor Planck, for your great presentation. My question was concerning your software, OpenCar. I've seen today a couple of presentations talking about different modules which are built on top of OpenCar, but are not actually part of OpenCar. I was wondering whether you have some plan for the future developments of OpenCar, if you think about including additional modules sooner or later, or
so there's no clear roadmap for that right now. So we are into modeling since 20 years, and this is the first time we actually released any code, I must admit. So, but all the carb utils, mesh tools, and OpenCarb has been redeveloped from scratch, and it's really available. The very advanced, the cutting edge stuff we're doing right now in the lab is currently not included. But over time, we will add stuff as soon as it, honestly, as soon as it's academically not a key instrument anymore. Once it becomes common, we will release more stuff. For the time being, we basically share code then with collaborators. If you have joint grants and so on, we share the code, or we share binaries, which is even more convenient. The project started recently, and it was a huge effort to put this together. So we are trying to get the community going, and we have not thought very carefully what will be included in next releases. I know there's a huge demand for reaction control and lead field, because that's a very nice model to use. For now, it's not included.
Okay, thank you. It was just a curiosity to see, just to check whether you have any plan, or we are going to see anything.
It's supposed to be a community modeling project, and we try to engage. So I think it's a very nice abstract framework now for doing all kinds of PD work. We hope it will attract the mathematical and numerical community to build on it, because you can do that easily. And we'll see, we're going to observe, whether it's picked up or not, whether people are making contributions or not. So far, 100% of the code has been developed by a company actually in AmeriCorps. So they're doing the bulk of the code writing.
Okay, thank you very much.
Thank you. Do you have more questions? I don't see more hands. Maybe Olaf Dussel again, or just me? Yes. If
there would be someone else, I would step back. But if there is no one else, then of course I think the major question from a higher perspective is validation. And you didn't talk so much about that, or not at all. I think the validation would mean you have to predict something, a measurement that you did not put into the creation of your model. And this prediction must be in some way orthogonal, because if you predict something that is very similar compared to what you already put into your model, it's trivial. It has to be completely different situation. For example, you parameterize your model with the sinus rhythm ECG, and then you predict the ECG of a premature ventricular contraction.
Yes, that would be a next step. I would not say I haven't talked about validation, because validation usually is you calibrate your model to observations you have. You can do an independent validation where you use data for validation you haven't used for fitting. So right now you're right, we are showing goodness of fit and not validation in your sense. But I must disagree, Olaf, in that regard, that it's not trivial to match the observations. It's highly non-trivial to match it. So here I disagree, but sure, further evidence is needed, then the predictive capabilities have to be shown, right? Absolutely, and but the model for doing that kind of work is now in place, because if you have heard before reaction diffusion bi-domain models, it's very nice, but if you want to do any of this work on such a model, you are doomed. It's way too expensive. So we currently finished the development of that, and there will be a lot of downstream work over the next couple of years. Mm-hmm. Also with you, hopefully, Olaf, within the Metal Care project.
I think we have on the long run to rely for this phase of validation also on invasive measurements. In the beginning of your talk, you said it would be beautiful to do every parameterization strictly non-invasive, and I was shocked, how would you do that? But I think for this phase of the project, we would definitely need, because I know from the inverse problem of ECG that there are so many ambiguities. So there are two completely different depolarizations on waves on the ventricles that lead to precisely the same body surface potential map. And that's
you are longer in the field than admittedly in the inverse field. I have not seen that. The ECG is a highly sensitive measure. Mm-hmm. And if you, in my model, if you're able to recreate the same ECG with two different activation patterns, mm-hmm. I'm the first to congratulate. I don't think it's not going to happen, because it's very sensitive. It can be similar. In the inverse, you have a very blurred source model. We have a highly precise source model, and every detail is reflected in the ECG. Usually it's filtered away and so on. But I think the other aspect is why I want to stay non-invasive. If computational modeling becomes a clinical modality, it has to work non-invasively. Mm-hmm. The invasive data, honestly, are not that great. Endocardial mapping in the ventricles, this is a scientific way of expressing a gut feeling. This is not a measurement in my view.
For the ventricles, you're absolutely right, but not so seldom. I think in our hospital, they have once per week a patient where they measure in the ventricles, and 2 patients per day where they measure inside the atria. So that the invasive measurements inside the atria are millions worldwide per day.
I'm rather counting on really massively invasive measurements in animal experiments. I know the activation sequence of a canine and the Purkinje system is different, but here, when you get a 3D resolution of the activation sequence, you can at least learn something. I still think if we have enough physiological understanding to set up the model and we replicate an ECG and we replicate a pacing sequence, I think we are very close to the truth. I don't think the non-uniqueness problem does not worry me so much.
Okay. Thank you.
Welcome.